Hello guys. Today we have a special show for you. 3 monkeys have escaped from the zoo to help you guys review some chemistry. What a treat.
What up peeps, my name's Justin Yee.
Stand that.
Hi guys, it's me, Zilong.
Hey guys, just saying, I am still a newbie. I do not know how to
Hey boys, in this unit we will be talking about bonding molecular structure. Couple things you need to know are that valence electrons are the electrons on the outermost shell of an atom, and those are the electrons that are involved within chemical bonding. Here's a periodic table, and as you can see, the electronegativity of elements increases as it progresses up and to the right. When you look at it, it almost makes you wanna. Let's explore the different types of bonds that exist in chemistry. First, we have the ionic bond. This is a bond between a nonmetal and a metal. In this bond, the nonmetal gains the valence electron of the metal, while the metal loses it completely. The nonmetal becomes an anion, while the metal becomes a cation. Next, we have covalent bonds. In this type of bonding, two nonmetals share valence electrons. Molecules of this type of bond can be single, double, or even triple bonded. Bond strength increases and bond length decreases as the number of bonds increases. So triple bonds have the strongest bonds, as well as the shortest bonds.
Vegeta, what does the scouter say about his power level? It's over 9,000! What, 9,000?
Metals undergo a special kind of bonding known as metallic bonds. They deposit their electrons into a sea of flowing electrons, which gives metals their malleability and electric conductivity. Lewis structures are visual representations of molecules that show what type of bonds are being formed. We form bonds according to the octet rule, in which the valence shell of each atom has a total of 8 electrons. There are a few exceptions though. Boron trifluoride, for example, a molecule of carbon dioxide can be drawn like this. A molecule of ozone can be drawn like this. Nitrogen trioxide has resonant structures. But we've discovered a new type of bonding. Behold, the Trinity bond. But it is highly unstable because of the formal charges on each oxygen atom. VSEPR diagrams can show the geometric shape of a molecule based on the number of paired and unpaired electrons. We have compiled a delightful tune to aid you in memorizing these formulas.
Valence shell electron pair repulsion.
I have
2 bonding pairs.
I have
0 lone pairs. Linear.
I have
3 bonding pairs.
I have
0 lone pairs. Trigonal planar.
I have
2 bonding pairs.
I have
1 lone pair. Bent.
I have
4 bonding pairs.
I have
0 lone pairs. Tetrahedral. Valence shell electron pair repulsion.
Woo! What a great composition. Next up, we need to cover the dipole moment in a bond. Because of the atoms' different electronegativities, electrons are focused in different regions of the bond. Take the classical polar molecule of water.
Well, you coming? Get us the blazes out of here! Turn this sled around!
Look there!
Trucks! They're ahead!
Hybridization is the process in which the mixing of two or more atomic orbitals form a new set of hybrid orbitals. It consists of mixing at least two non-equivalent atomic orbitals, s, p, or d. Hybrid orbitals have very different shapes from atomic orbitals. The number of hybrid orbitals equals the number of pure atomic orbitals used in the hybridization process. Covalent bonds are formed by overlap of hybrid orbitals with atomic orbitals in hybrid orbitals. To find the hybridization of an atom, draw a Lewis dot structure and count the number of effective electron pairs around the atom. Then subtract 1 and match it to sp, sp2, sp3, dsp3, and sp3d2. So in molecular hybridization, there's a couple more bonds you might need to know. Sigma and pi bonds. Sigma bonds are formed in an overlap of n-to-n orbitals, and pi bonds are formed above and below the plane of the molecule. A single bond has one sigma bond. Double bonds have one sigma and one pi. Triple bonds have one sigma and two pi bonds. Molecular orbital theory. Bonds are formed from an interaction of atomic orbitals to form molecular orbitals. So we developed a new diagram for molecular bonding. In this diagram, the y-axis represents the energy of the bond, and the x-axis is basically just the two bonds together. Anti-bonding orbitals are higher up in energy because they are less stable. These exist because electrons might not be in the bond. As elements with more valence electrons appear, the two p orbitals and the 3s, etc. will fill up. Take notes of how many valence electrons each element will use for bonding and what molecular orbitals they will fill up.
So that's all I want to say. So thanks, I guess. And I am still a newbie.